Welcome once again in the class of design of steel structure. We are learning the design of column bases. In last lecture, we have learned how to design a slab base. In today's lecture, we are going to see how to design a gusseted base. I am Mr. S. Ule, Assistant Professor, Civil Engineering Department. Before moving to the gusseted base, you'll see the small uh, part of this foundation, that is foundation bolt. So when foundation bolt are needed, actually we are providing the foundation bolt uh, at least for the nominal also, because sometimes due to some reversal of stresses or due to some tension, there might be some tensile forces into the foundation, so that the column will move or lift from the foundation. So to keep the column in the position, we are going to provide the foundation bolts. And again, whenever the bending moments are present, foundation bolts of adequate size must be designed to hold the column down to the concrete pedestal. Now, let us say the column is subjected to axial load P and a bending moment M. The column will try to overturn either about it's any one of the axes passing through the bolts, depending upon whether the movement is clockwise or anti-clockwise. The axial load provides a counteracting stabilizing moment, that is equals to px divided by 2. So when the clockwise movement act as shown in this, here you can see this is the force and this is the moment. So when this clockwise movement act, the bolt A and B, that is these two bolts, will actually if you see the bolts over here, consider this thing, that is these are A and B and these are C and D. So further by magnifying thing, we'll see here. So this A and B bolts are subjected to uplift, and this is C and D are for the thrust. So these uplift and thrust form a couple, that is which are this x distance apart. So these will form a couple, that is P and P, that is 2P1x. These are 2P forces and these are 2P1 forces which are acting opposite. So they will form a couple, and the intensity of that resisting couple is 2P1x. Hence, the total stabilizing moment under the action compressive force P and movement M will be Px by 2, that is this one, that is stabilizing moment, plus 2P1x, that is this another stabilizing moment. So for equilibrium, we are equating that moment to these two forces, that is M equals to Px by 2 plus 2P1x. So the P1 will get, that is M divided by 2x minus P by 4. So P1 is nothing but the uplift force in the bolt, and x is the distance between the bolt lines. So now for this P1 force we have to design the bolts. So now first, what are the design procedure of this thing? First we need to calculate or compute the uplift force P1 on the bolts by using this equation. Now they calculate the area of the root of the bolt by this, that is As equals to P1 divided by sigma Tf, where this As is the area of the bolt at the root of the thread in mm square, and sigma Tf is the permissible tensile stress in the bolt, which is 120 MPa. So note has been given. So the while choosing the bolt, we have to take the diameter of the bolt, that is 20 to 36 mm. So this is the procedure of designing this foundation bolt, which will help us to keep the column at its place. Now the gusset base or gusseted base. When the load over the column section is too large or axial load is combined with the bending moment, the gusset base is provided. The gusset material used in the base to increase the bearing area, consequently reducing the thickness of the base plate as compared to the slab base. So in this gusseted base or gusset base, what we are doing, initially in slab base we used to provide only the column on this base plate, but in this case we are increasing this bearing area by providing this gusset. So what this will do, this will increase this the bearing area or the load transferring area, so that we will have a smaller size of the plate, or it will help to transmit a more kind of uh, or more load on the particular base. So here you can see this is the column, this is the gusset plate, this is the gusset angle. Again foundation bolts are there and base plate is there. So these are again web cleats. In case of shear we have to provide the web cleats also, and this is the concrete pedestal. If you see the section over here, so this is the plate, this is the angle, and this is the column we have attached with the help of these bolts, and this is the side view. Here you can see this gusset plate. So now the design of the gusset base. Again, one more thing I would like to add, in our last, that is in case of slab base, we have the critical section over this particular face of the column. In the gusseted base, what will happen? The critical section will be here, that is here. That is, you can see this critical section 1 1. So it is at the face of, or uh, at the edge of this particular angle, and angle will also help to take that bending movement also, that we will see in the procedure. So the following the procedure will be adopted for the design of the gusset base. So assume the suitable allowable bearing pressure on concrete depending upon the grade of concrete. The area of the base plate is computed by A equals to P divided by allowing bearing pressure in concrete. The size of the gusset material is assumed. The gusset plate should not be less than 16 mm in thickness. The gusset angle is chosen so as to accommodate two rows of rivet in vertical leg. As here you can see, we have to accommodate these two rows in the vertical leg and one row of bolt in the horizontal leg. Subsequently, an unequal angle section is provided. The thickness of the gusset angle should be almost same as that of gusset plate. The length of the gusset plate material is normally kept equal to the length of the base plate parallel to the flange of the column. So the dimension of the base plate parallel to the web, that is L equals to depth of the section plus 2 into thickness of the gusset plate plus leg length of the angle and overhang. As here you can see. So while deciding this length, what we need to do, we have to check the depth, then thickness of this thing, then length of this leg of the angle, and this small overhang here you can see. The overhang should be kept minimum about 1 centimeter from the gusset angle 2. Now the dimension of the base plate parallel to the flange, that is equals to B equals to A divided by L. Now the intensity of bearing pressure W from the concrete below the base is worked out by using this expression, that is W equals to P divided by A1, where A1 is the area of base plate provided. The thickness of the base plate is computed by equating the moment at the critical section, as we have discussed earlier, to the moment of resistance of the gusset at that section. The critical section is assumed to lie at the root of the fillet of the angle section for unit width of the plate. So the bending moment at the critical section 1 1, as we have seen in this diagram, and this overhang they are mentioning it by C. So the bending moment 1 1 at critical section 1 1, that is M equals to WC square divided by 2. The moment of resistance at critical section 1 1, that is MR equals to Z into sigma bs. Z is nothing but the section modulus. So that becomes 1 by 6 into 1, which is the width, and into T square into sigma bs. So the moment of resistance is T square divided by 6 into sigma bs. So again by equating these two moments, what we will get, M equals to MR So WC square divided by 2 equals to T square by 6 into sigma bs. So the thickness T equals to C into under root 3W divided by sigma bs, where T dash is equals to T minus thickness of the angle section, because here we need to consider this angle thickness also, and by deducting this angle thickness we will get the plate thickness, where this W is the intensity of pressure from the concrete under the slab, C is the portion of the base acting as a cantilever, T dash is the thickness of the base plate, P is the thickness of the base plate at the critical section, that is thickness of the base plate plus thickness of the angle section resisting the movement at critical section, and sigma bs is the permissible bending stress in the slab base, that is 185 MPa. So the connection are designed for the forces to which the column is subjected. If the column ends and gusset material are not faced or machined, the complete bearing, the fasteners are designed for the total forces to be transferred. And if they are faced or machined for the complete bearing, the 50% of the forces are transferred directly by the column and 50% through the fasteners. Then the diameter of the rivet is assumed and rivet value is computed as we have learned earlier in single shear and bearing, and the number of rivets are worked out by n equals to p dash divided by rv, where n is the number of rivet, p dash is the force on the fastener in newtons, and rv is the rivet value in newtons. These rivets are provided to connect the gusset plate with the column flange. The height of the gusset plate depends upon the number of rivets to be accommodated. The same number of rivets are provided to connect gusset plate to the gusset angle. Nominal size diameter rivets or bolts are provided on the horizontal leg of the gusset angle to keep the column in the position. Now, what we are going to do, we will solve the same problem that we have solved for the slab base, and we'll check the whether the base plate of the same size required or less size is required. So area we got is 0.75 meter square. So assume the thickness of the gusset plate 16 mm and ISA 150 by 115 into 15 mm gusset angle, one on each column flange should be provided, that we are assuming. Now the minimum width of the base, that is the width of the column is 350, because what we have this ISSB 350 here, plus 2 into 16, that is thickness of the this gusset plate, plus 2 into 115, that is the length of the leg of the angle, and that becomes 612 mm, which is the minimum width of the base. So we are taking 630 mm. Now the projection beyond the gusset angle is 630 minus 612 divided by 2, that becomes a 9 mm. The length, so the length we are calculating by dividing the area divided by the particular width, so that becomes 1190.47. We are providing 1200 mm. So the provider plate of the 1200 by 630 mm. Now the pressure on the plate from below, that is W equals to 3000 into 10 raised to 3 divided by 1200 into 630, so that becomes 3.968. Now the length of the base plate as a cantilever, so this 115, because we are taking the movement or critical section is at the root of the this particular fillet of the angle, so 115, which is the length, plus 9, which is the overhang, and minus 15 is the thickness of the angle, so that becomes 109. If I draw the diagram over here, this is the angle, this length is, this is 115, and this thickness is 11 point or 15. So we are taking a section over here, and further this is of 9 mm. So what we need is this distance. So that is 115 plus 9 minus 15. So that becomes 109. So combined thickness of the base plate and gusset angle at the critical section. So that equals, we are using the formula, that is C into under root 3W divided by sigma bs. So that is 109 into under root 3 into 3.96 divided by 185. So that becomes 27.64. So we are providing at 28 mm. So thickness of the base plate is 28 minus 15, that is thickness of the angle. So that becomes 13 mm. Now we are providing 16 mm thick base plate, as it should not thinner than the gusset plate. So let us provide 24 mm diameter power driven rivets. So the gross diameter is 24 plus 1.5, that is 25.5. So strength of the rivet in shear, that is pi by 4 into 20 d square into 100, so that is 51. And strength of rivet in bearing, that is d into d into t, that is thickness of the flange, and into 300, that is sigma bf. So that becomes 88.74. So minimum of these two, the rivet value is 51 kilonewton. So let us assume ends of the columns are machined. So 50% load has been transferred with these fasteners. So n equals to 1 half, that is 50% P divided by this RE. So 1 half into 3000 divided by 51. So the number of bolts will be 29. So we are providing 32 bolts. So provide 16 24 mm rivets on each face of the column, and the same number of rivets are used to connect the gusset plate to the gusset angle. So the rivets are provided in two rows. So minimum pitch we know, that is S equals to 2.5 into 5. So 2.5 into 24, that is 60 mm. So for 24 mm diameter rivets, the edge distance is 38 mm. So provide 40 mm edge distance. So we are taking the check for the tearing of the plate. So we have the formula, that is rivet value equals to S minus D into T into sigma at. So uh, by putting all these values, we need to find this S spacing. So we'll get the rivet value 51 divided by this T into sigma T, that is 11.6, which is the again thickness of the flange, into 150 into sorry plus 25.5. So the spacing will be 54.85, and it should not be greater than 60, hence it is okay. So height of the gusset plate, that is 150 plus 2 into 40, that is edge distance, plus 60, that equals to 290 mm. Length of the gusset plate, that is length of the base plate, that is 1200 mm. So provide a gusset plate of 1200 into 290 by 16 mm. This 150 is the length of the angle, leg length of the angle. So this way it looks like. So this is ISHB 150. This is the gusset plate of 1200 by 290 by 16 mm. This is the gusset angle, that is 150 by 115 into 15. This is the base plate of 1200 by 630 into 16. So we are providing the these rivets in this way, that is 8 rivets over here, these 8 rivets over here, and same way these total 16 rivets and these total 16 rivets for the these connections. So this is all about this gusseted base. This is the design of the gusset base. Thank you.